While you're waiting for the others to join, is there any doubt about whatever we have done the course so far? Tutorial, anything for that matter? Okay. Now the contents is the approach of teaching the course going well. Are you sort of comfortable with the style?
Yes, sir.
What to do? Okay. In case you have any suggestions or if you have any issues, please feel free to let me know. Idea about midterm pattern, Somin, I have absolutely no idea, to be honest. I'm not just trying to tease you guys. I've really not even started thinking of the midterm. Okay, so the short answer is no. And just give you a general guideline, understand the concepts well, and if you have understood them well, then I think the pattern doesn't really matter. Almost certain that this answer of mine is not going to help you at all. But yeah, so yeah, I've not started even thinking of the midterm as of now. In fact, I think as of now, at least, the question paper will be common for both sections. That's the way I understand it. I have not even discussed this with Rahul as of now, but I believe it will be a common question. That's as far as I have thought about the midterm. Anything else? I mean, any suggestions? Are the lectures fine? Is my handwriting clear enough? Anything I've been think about the course you think is not going well or is going well, so that I should continue doing the same thing. You guys are experienced in the sense that this is your third online semester. Solutions of the tutorials, I think we are discussing them in the tutorial session itself. As far as I think, we are discussing each and every question. So I don't think we'll be making written solutions available, but in case you have specific doubts, you should feel free to reach out to any TAs or us. So let me just complete what I was saying. I think this is your third semester online. And you are more experienced than me in the sense that I teach only 1 or 2 courses every semester. So this is possibly my 4th or 5th course. You guys have already done 10+ courses online. So there may be some features of instructors that you may have enjoyed and that may help you in this course. If that is the case, please let me know. Yeah, I'm not promising I will incorporate those, but at least I will think about it. I understand studying online is not the easiest thing to do. And teaching online, of course, is also not the easiest thing to do. It could have been much more interactive if you guys were here on campus. Have to make do with this arrangement for now. So that's why, in case there's anything that I could do to make it a more enjoyable experience, more worthwhile experience, then I will be happy to hear that from your side. Okay. Simply nothing apart from these 2 questions of the tutorials and midterm, then we can begin today's class. students in the meeting. Okay, let me first call out the scribes for today's class. That is group 9, ID number 50. Are you there? 5050, are you there? No. 51. ID number 51, are you there? 52.
Yes, sir.
51. Who is 51?
Yes, sir. Dhwani here.
Okay, 52.
Yes, sir.
53.
Yes, sir.
54.
Yes, sir.
She. 55. 55, are you there? ID number 50. Okay, so let's begin. The details. So we're talking about group homomorphism, right? So today is the class when we define what we mean by homomorphism. Before we look at the 4 examples shown in the slide, right, what does the word homomorphism mean? Any idea? What does the word morph mean? And what does part of the word homo mean? Anybody? What do we mean by morph? You may have heard of the word morphism or morphing, right?
Mixing.
Who is this? Once again? Jaimesh is same form. So form, right? Morph or morphism basically refers to form or shape or structure. Okay, and homo of course means same. So in all these latest Hollywood and maybe even Bollywood movies, you may have seen one character deforming or morphing into the other character, right? Typically, when you look at both the characters, right, one from which the morphing begins and the second into which the morphing ends, they usually are similar in the sense, yes, one human form morphs into the other, whether he's male, female, or different structures, right? Different physical attributes. That is possible. Maybe even a human being into an animal you may have seen. But usually we have not seen, at least I have not come across a morphing scenario where you have a human being that morphs into, let's say, an inanimate object, maybe a ball or something like that. Usually you would have very similar structure, okay, between the characters from which the morphing begins and into which the morphing ends. Okay, so the reason typically is because the first and the last character, right, they have similar structure. Okay, so perhaps borrowing from that, we have a similar concept in groups, and in fact in several areas in math, especially algebra, and something called homomorphism, which means that you're trying to see that these 2 different examples that we are studying, and they have the same structure. So structure, of course, I hope reminds you of our first lecture. Okay, structure in the sense that you're not interested in the particular elements per se, but we are more interested in the relationships between the elements. And as far as a group is concerned, the relationship is basically governed by the group operation. Okay, now let's take a look at the four examples in the slides. There are four groups, each containing four members, okay, four elements. Now think about the four different sets. Right? The elements that these four sets have are very different in nature. So Z4, it has integers going from 0 to 3. Right? C4, this set, it doesn't have integers, it has complex numbers. Moreover, Z4 comes with the group operation, which is addition modulo 4. C4 comes with multiplication between complex numbers. So if I consider these elements, right, the elements are like chalk and cheese or apples and oranges, right? They're very different. Especially if we look at the other two examples, Z2 cross Z2, the Cartesian product of Z2, where the group operation is element wise modulo 2. This is a tuple of integers 0 and 1, all tuples of integers 0 and 1. This and integers or complex numbers, these four complex numbers, they are very different. Similarly, the fourth example, symmetries of a rectangle. This is a new example which we have not discussed earlier, but I hope it is clear what I mean by that. Okay, it also has four elements. So the identity transformation, because it leaves the rectangle to where it was. Rotation here denotes rotation by 180 degrees. Okay, so that also will leave the rectangle as it is. Right, and then you have the horizontal flip and the vertical flip. These are the only four transformations that will leave a planar rectangle as a planar rectangle, right? So these four transformations, along with the usual transformation composition, this also forms a group. Here the elements are transformations. They have nothing to do with integers, complex numbers, tuples of integers. So all these four examples have very different elements. Right? The nature of elements is very different. But still, if we look at the interrelationship between elements of these four groups, right? Are they really very different? That's the question. Are these groups really different? And I should quantify what do I mean by really different. I mean that is the structure different. Okay, so again, by structure, remember, said that we are interested in the interrelationship. So more specific, let's look at these two examples shown on the left hand side of the slides. So do you think the interrelationship between these four elements over here and these four elements over here is any different? Does anybody want to try this? Is the interrelationship any different between these two sets and this set operation?
Sir, in second means multiplication on complex number, if we interchange row 2 and 3, then we can see similarity between these two.
We interchange row 2 and 3. How? I mean, how did you come to this conclusion?
Because identity element in both group are at same position.
So you mean the identity in Z4 is 0, the identity in C4 is 1.
Yes.
Okay, then?
Oh, sorry, sir. I understood it wrong. Sorry, sir.
It's okay.
0 maps with 1, 1 maps with I, 2 maps with -1, 3 maps with -I.
So 0 is the same as 1, right? So once again, remember, we are looking at interrelationship between elements, not the elements themselves. So in other words, if I want to figure out whether the relationship between elements are the same, then I can basically relabel, right?
Sir,
I
they are
think,
all symmetric. They all form symmetric matrices.
is that enough, right? So they form symmetric matrices, that's fine, but what we are looking at is the interrelationship, right? So
There is a one-to-one relationship for all elements, both examples.
so right, Pandan, yes, that's right. Let me try to make it more simpler to understand. So if I'm sort of, let's say, let me see. So if I'm not interested in what these specific elements are, right, are the names of these elements that is given over here. I'm calling this element as 0, this as 1, this as 2, this as 3. Are the names any important at all?
No, sir.
Right? If I'm only interested in how these elements sort of change into each other using the group operation, right, then I'm not interested in what are the names given to these elements, right? So I can as well call this 0 element as 1, right? I can call this 1 element. I hope the color is visible. Not, maybe I'll change it back to white. So I call, instead of calling this element as 0, I can call it 1. Instead of calling this element 1, I can call it I. Instead of calling this element 2, I can call it -1. And instead of calling this element 3, I can call it -I. And then use the interrelationship that is given over here in this table. Right? So for example, 0 plus 0 gives you 0, right? Yeah, I'll write it down over here, right? 0 plus 0 gives you 0. Now 0, I have decided to rename it to 1. So wherever 0 occurs in this table, I should replace it and call it 1. Spacing. Okay, where else do you have 0? So in the group table, this is again a place where you have 0. So I should rename it 1. This should be renamed as 1. This should be renamed as 1. Next, I've decided to rename 1 as I. Okay. So again in the group table, find out where do you have 1 and then rename that 1 also as I. And repeat the same for 2 and 3. 2 is renamed to -1. 1, 1, -1. And finally, 3 is renamed to -I. I, minus I. Right now, forgot these 2, so this 2 is 2 -1. Right now, if I look at this new table that I've drawn in white, compare it with this table given over here, is it any different?
No, sir.
No, sir.
They're the same, right? That is what I meant by same structure. Because once again, I'll repeat this the 100th time. not interested in what the specific elements are. I'm interested in the interrelationship between elements. Since that is what interests me, what is the name that I give to those elements does not matter. Okay, so in that sense, Z4 addition modulo 4 and this C4 with complex number multiplication are one and the same. Okay, so from the abstraction point of view, how it helps us is if I want to sort of derive something with respect to the interrelationship of elements in C4, right? And if I'm finding it tough to deal with this particular example, C4 with complex number multiplication, since the interrelationship between C4 is the same as that of Z4 with addition modulo 4, I can as well study the interrelationship of Z4. Okay, you are going to get the same results. You're going to be able to derive the same properties. If, once again, that's a big if what matters to you is only the interrelationship and not what those specific elements are. So that is what is abstract math as an example. We are now going to look at groups not as separate examples, but groups. We are going to look at them only keeping in mind what is the interrelationship. That is the only thing that matters to us. So therefore, what we can do is rather than studying these two examples separately, we can study only one of them or something similar, right? But whatever we are able to derive from this one example, as far as the derivation uses only the interrelationship between elements, whatever results we can derive then is equally true for all these examples as well. Okay, so that is sort of the importance of studying homomorphism. Is that clear?
Sir,
Yes.
sir, here we have one-to-one correspondence for all elements. So here we can define some function like y equals e raised to ix, so that for all x belongs to Z4.
Yes. So, right, that's right, Vandan. But just have some patience. As of now, I'm just discussing this with an example. I have not formally defined what a homomorphism is. Right. So just wait for a couple of minutes. The definition of homomorphism will be discussed in the next slide.
Okay.
Right. But I hope all of you realize the importance of homomorphism. Right. It helps us reduce the work tremendously in the sense that these two examples shown over here, and of course you can create several more examples, right, which have the same structure. So rather than waste time in studying each and every example separately, this concept allows us to sort of treat all these separate examples as if they are one and the same. Whatever you derive about one example applies equally well to all these examples, as far as the derivation uses only the interrelationship. Okay, that's an important condition. All right. So similarly, what do you think about these two examples, Z2 cross Z2 and symmetries of a triangle? Oh, sorry, symmetries of a rectangle. Are these two groups really different? Okay, whenever I ask you this question with an example, you should remember I am interested only in the interrelationship. Therefore, is there a way in which I can rename the elements, right, to the elements of a different set and replace all these names by the new names I have given in the original group table and see if the group tables are any different? Okay, so Yes, can somebody sort of give me how should I rename the elements of this set Z2 cross Z2?
Sir, 0, 0 with I here. 0, 1 with R.
0, 1 with R.
1, 0 with FH. And 1, 1 with FB.
Right, now go ahead and replace these names in the group table here also, and see that this table and this table are the same. Okay, and then finally, of course, the last step to see over here is, since what is the name given to us does not really matter. Okay, instead of using this symbols, I can just introduce some abstract symbols, E, A, B, C, right? Just to emphasize the fact that these may be numbers, these may be functions, these may be any damn thing, right? The only thing of interest to you is the interrelationship. C, E, A, B, C, right? And that will fill this up. C, right? What would be this? I could just look at this group table.
B, C.
C, E, then E, C,
C, E.
A, C, E, A, B. Okay, it doesn't matter what is the name we give. E is just a preferred notation for identity, which is why I have denoted this as E, but I mean, I can use any other notation that I can imagine, like, to denote this element. Okay, and then whatever I derive about this set using these interrelationships will equally apply to both these examples here, this as well as this. So is the idea of homomorphism clear? Same structure, right? I mean, whenever you hear the word homomorphism, first thing that should come to your mind is same structure. Okay, so now let's go ahead and define formally what is a homomorphism. So basically, whatever we did with these two examples, we are now going to define this. So group homomorphism. So let's say I am given two groups. G1 is a group with dot as the group operation, G2 with the asterisk as the other group. Okay, let these two be two groups. Then a function from should be G1 to G2. Right. So what is this function encoding? As far as what we did with the examples is concerned, it's just the renaming, right? So a function f that maps elements of G1 to G2 is said to be a homomorphism if for every pair of elements in group G1, f applied to the result of the binary operation between A and B is the same as first applying f to A, getting an element in G2, then applying f to the element B, getting an element in G2, and then performing the binary operation between FA and FB in G2. Okay, so please be careful with these notations. This asterisk is the group operation defined in G2. And this dot is the group operation on G1. Is the definition of homomorphism clear? What this basically, this equation states is that F preserves the group operation. Whether you first perform the group operation in G1 and then apply the function F, or if you first apply the function F and then apply the different group operation, the resulting element has to be the same element in, of course, remember both sides, the element will be in G2. And this should happen not only for a specific pair of A and B, this should happen for each and every pair of AB in the group G1. Any doubts here? The definition understood? Maybe let's look at a few examples that would make it more clear. And I want you to see is that you have previously used homomorphisms even in school, okay, without knowing that these are homomorphisms. So let's look at this example. Unless some of you have doubts with the definition. Okay. So let's consider this function F. What are the groups? This is the set of non-negative, sorry, this is the set of positive real numbers. Okay? Set of positive reals. 2, this is just the set of real numbers. Okay, what are the group operations on the set of positive real numbers? I have real number multiplication as the group operation. Okay, I hope all of you agree that this is a true. Okay, and the second group G2 is my G1. Second group G2 is your usual real numbers with real number addition. Okay, what is the function that I am considering? F maps any positive real number x to its natural log. Okay, that's how I'm defining F to be. Can you see, can you verify whether this F is a homomorphism or not? If I have to check whether this definition of F is a homomorphism or not, what do I have to check? The definition for all AB in group 1. What is group 1? Positive real numbers. Okay, what is F of A dot B? What is dot? It's your real number multiplication. Okay, this by definition is natural log A, sorry, A into B. What is this equal to?
Log A plus log B.
Log A plus log B. All of us know this, and all of us have been using this in order to simplify our calculations, right? Even in school. So since this is true, and what is natural log of A? That's nothing but your F of A. Plus, which is the group operation on G2. Natural log of B is F of B. Okay, so therefore, what have we proved? Just shown that the natural log is a homomorphism. Okay, and all of us know the practical importance of the natural log. Any doubts with this example?
Sir, here F may not be one, may not be one. Can it be anyone?
So in this case, would F not be 1, 1?
No, sir.
Can we have?
From the definition, will it be
Okay,
always?
yeah, sure. No. So we'll look at examples. Yes. But so your doubt is understood. I'm going to answer that in a few minutes. Is there any doubt with this example specifically? Okay. Let's move on to the next example. How about this function? F from G2 to G1, right? If G2 was set of real numbers with addition and G1 was set of positive reals with real number multiplication as the group operation, I can also define a function from R plus with real number multiplication in this way. Fx equal to exponential of this x. Is this a homomorphism?
Yes, sir.
Yes, sir.
Okay, so try to prove this, or maybe I'll prove it for this particular case. For all a b in R, f of a dot b. What is dot here?
Plus.
Plus.
Plus. This is exponential of a plus b. This, from the property of the exponential function, we know is equal to a multiplied by xp. Xa is nothing but f of a. Xp is nothing but f of p. Okay, please be careful with these group operations. Here on the left hand side, the group operation is the group operation for the first group. On the right hand side here, this is the group operation of the second group G2. Okay, so we have basically proved that the exponential is also a homomorphism. What is the relation between these two examples?
Inverse.
They are inverses of each other. Okay, so that's again something that we'll look into towards the end of the class, hopefully. Okay, let's look at another example. The two groups need not be different, right? We can also have a mapping from one group to itself. So the groups we are considering is Z plus to Z plus. Okay? Integer addition. And function f is defined as fx equals 10x. Is this a homomorphism? So I do not recall who asked this question, whether f is 1 to 1 or not. You can see this as an example, although in this case also it is 1 to 1. It's maybe there's the next example will show a counter example. Anyways, is this function f a homomorphism?
Yes.
Yes,
Yes,
sir.
sir.
Yes. How will you show that? For all AB in Z plus is f of a plus b. Use the definition of f.
N into A plus B.
N into a plus b. This is equal to Na plus 10d. Remember, this multiplication by 10 is not a group operation. Okay, so don't get confused there. Okay, the group operation for both groups is addition. Okay, so then 10a is of a, 10b is of b. Okay, so therefore is of homomorphism. All right. Let's look at another example. And by the way, what is the difference between the first two examples and this example?
The third example cannot be inversed. We cannot have its inverse, but the first two examples have inverses. They are inverse of each other.
So why can't the third example have an inverse?
It is not onto.
Sir, for in
Okay, so it's trying to give you different kinds of examples of homomorphism. The first two cases, it was bijective. Third example, F is not onto. Let's look at the example. So F maps the first group. And what is the first group? R star. I hope you remember what is R star. Is R star? Anybody recall this?
R minus
0.
0.
R minus 0.
Minus. With your usual real number multiplication, right? That forms a group. So that's your first group. Second group is the set of only these two elements, -1 and 1, equipped with multiplication, usual real number multiplication. Yeah, I hope you can see this is a group. Okay, now here you can see these are very different groups in the sense that the first group has infinitely many elements, second group has only two elements. Okay, how am I defining this function? So F maps all negative numbers to -1 and maps all positive numbers to +1. Okay, that is how my F is defined. Right down here again. -1, x negative, equal to +1. Is this a homomorphism?
Yes, sir.
Okay, so this time I think I leave this as an exercise to show that F is a homomorphism. Again, what is the nature of this function? Is it one-to-one? Is it onto?
Many to one and onto.
Many to one and onto. It is onto, but not one to one. Okay, so I hope I forgot who asked this question. I hope now it should be clear that this function F, the homomorphism need not be one-to-one, it need not be onto, it can be just about anything. Because if you carefully look at the definition of group homomorphism, it only says that the structure should be preserved, nothing else. Okay, let's look at another example that I don't know if you have seen this or not. So F maps the first group. What is the first group? GLNR. What is GLNR? I think we have defined this in maybe the first two classes. What is GLNR?
General linear groups.
General linear group. And what does it mean?
N cross n
Matrix of
matrices
n
with
cross n.
non-zero determinant.
Okay.
And values are
Then invertible matrices with entries from R. Okay, good. So therefore, what can we say about the determinant of any element of GLNR?
Non-zero.
Non-zero. Now let's look at this function. F from GLNR to R star with multiplication. Definition is F maps. So F is nothing but the determinant mapping. Is this a homomorphism? This you may not know, but determinant follows this rule. Whenever A and B are square compatible matrices, which means they are of the same size, in that case, this is true. The determinant of the product of matrices is equal to the product of the determinant of the two matrices. Okay, so this is something maybe we'll prove, when we look at linear algebra in the second part of the course. But for now, in case you're not aware of this, just accept this. Okay, once you accept this, I hope you can see why the determinant has to be a homomorphism, right? Basically, we have proved this. Okay, remember the notations here are same, but they are completely different as far as the group operations is concerned. First group, this times or X stands for matrix multiplication, and in G2 R star, this time stands for the real number multiplication. Okay, is that clear? Doubts with any of these examples? Sort of tried to give you all different kinds of examples. One-to-one, onto, not one-to-one, but onto, but not one-to-one, matrices. So, hopefully covered several different examples. Is one very easy example to see that I have not yet given. It's the next thing. Let us take two arbitrary groups, okay, G1 and G2. How about this function? F maps all elements of my group 1 to the identity element that I'm denoting here by E2 in G2. The identity element of G2. Is this function a homomorphism?
Yes, sir, it is.
Right? It's sort of easy to see because in both sides you'll have nothing but the identity. Right? It doesn't matter what is A dot B. For any A dot B, F of A dot B will always be E2. Similarly, for any A, FA is E2. For any B, FB is E2. E2 star E2 is E2. So of course this is trivially true. Yes, so in some sense this is, I think when we started out looking at the examples in the first slide, it looked to be exciting. This sort of deflates on the excitement by trivializing it. Okay, so for all good homomorphisms, I'm yet to define what do I mean by good homomorphisms, but for all interesting homomorphisms, I think we would want to put some restriction on how this function f should be, right? Because as this example shows, I can map every element to the identity element. Yes, it is a homomorphism, but we cannot sort of do what we aimed to do, in the sense that we would want to study group 1 as if we are studying group G2. That cannot be done here simply because this function maps everything to identity. Right? So it doesn't really bring out the group G2 in its entirety. Okay, but it still is a homomorphism, and this homomorphism is what is called the trivial homomorphism. Okay, no matter what your group 1 and group 2 is, no matter what are the binary operations defined on them, okay, this map is, or this function, always a homomorphism. Okay, but of course it is a trivial homomorphism. Okay, in the sense that, I mean, it trivializes the group G1 by mapping everything to only the identity in group G2. Okay, I hope I've made it amply clear why homomorphism must be sort of put under more constraints to make it more interesting, or why homomorphisms are not always sort of interesting. Right? Yes, they do preserve structure. This example shows it doesn't really bring out the structure of G2 or G1. Right, but before we sort of make homomorphisms more interesting, right, let's try to derive some properties in general about any homomorphisms. Okay. Any questions so far? And just to make my job easier, right, I'm going to suppress these group operations. They are sort of a time consuming, right? So I'm going to make my life easier. I just write AB, right, for A dot B, and I write FA, FB in place of FA star FB. This might create a confusion, but I hope it is clear. Whenever you perform group operation between FA and FB, it has to be the group operation of the second group, G2. Whenever you're performing a group operation between elements of group G1 AB, it of course has to be the group operation defined on G1. Okay, so again, I hope you've understood. This can lead to confusion, but always carefully look at what are the elements between which you are performing the group operation. Any doubts? Okay, let's derive some interesting properties. Some of these you may have already observed from all examples that we have seen. Let's say F is a homomorphism between two groups, G1 and G2. Then, what is F of E1 equal to? Where E1, of course, denotes the identity of group 1. What should this be? Anyone?
E2.
E2.
E2. Why? So, proof is not very complicated. Let for any element A in group G1, right? What is F of A? F of A is the same as F of A even, right? And what is F of A even? Use the homomorphism property. This would be equal to
F of A into F of E1.
A of even. This has to be F of A, right? And that is how we began. And this is true for every element A. So, of course, you can maybe make it more easy to follow by saying this is equal to F of A. F of A is the same as F of A into
f of e2.
F of E2. That is what I was going to write.
Yes,
I
e2.
stopped just in time, right? So it's E2. And then by cancelling out f of a on both sides, we have of E1. Okay. So if F is a homomorphism, it must map identity of one group to the identity of the other group. Cannot do anything else. And again, if you have not observed this in all these examples, you can do so now. What is the identity in the first example in R plus times? Is the identity here?
0.
1.
Can it be 0? It's 1.
One.
So what is log of 1?
0.
That's 0.
0. That's nothing but the identity of R with plus. Okay, the same holds true for exponential. Maybe let's consider this case. What is the identity in R star? It's again 1. Right? So where does F map 1 to? F maps 1, since 1 is positive. So F of 1 will be equal to 1, which is the identity element of this. Okay, so let's move ahead. So F of E1 has to be E2. What else? So identity gets mapped to identity. How about inverses?
Inverses should also map to inverses.
Right. So let's try to prove that. We claim F of A inverse should be F of A inverse. Okay. How are we going to prove this? Can you try to prove this? Anyone?
Sir, f of A inverse is equal to f of E.
Of A inverse is equal to F of E1.
E1 and
Okay.
f of A inverse is f of A into f of A inverse.
A inverse.
Hence f of A inverse is equal to f of A whole inverse.
No, so you have to first write that F of E1.
F of E1 is equal to E1, E2.
Therefore, F of A inverse. And by the way, this you should also sort of write this equal to this into this. Okay. So for this, just write E1 as A inverse A. Okay. So therefore, F of A inverse is equal to A all elements. Right, let's move ahead. Yeah. How about this? I take any arbitrary element A of group 1, right? And I perform binary operation of A with itself n times, and then apply the function f. What should I get?
f of A raised to power n.
F of A raised to power n. Let's try to prove this. It's very easy. Anybody?
Let's go. F of A is equal to
F of
A into n times.
A raised to n. A times n.
F of A, F of A, F of A.
Here you're sort of using the homomorphism definition n times.
Yes, sir.
Be careful here. This is but in the power. Okay. Fine. How about the order? Like if order of some element A in group 1, I must write this, element in group 1, and its order is n. What can you say about the order of f of A in G2?
It also n.
Once again,
It should also n.
it should also be equal to n. Can you prove that?
Yes, sir. Here order of A is n, means A raised to n is I1.
There. A raised to n is E1.
E1.
Okay.
Then we know that f of A raised to n is f of A raised to n.
F of A raised to n is
Is f of A whole raised to n.
okay. Whole raised to n, and this has to be f of E1.
F of E1, which is E2.
E2. So
Order of f of A is n.
how did you conclude that?
Because sir, f of A raised to n is identity. So
So
that's
does that mean that
Sir,
is the order?
before that there is no
F of A
identity.
belongs to G2.
Sorry?
We will have to show n is the smallest such number.
Exactly. Can you show that?
Yes, sir, because if a power n is equal to E1 and n is order of A, so n will be smallest for which a power n will be identity.
Yeah. Okay. So n is the order of A. No problem about that. Right. So n is the smallest integer such that A to the power n is even. But how can you show that n is the smallest integer for which f of A to the power n is E2?
So then n will also be smallest for f of a whole power
Why?
n.
I mean, you have to show that, right? You cannot
No,
just
because
we
it is
consider that. We will consider that for some I less than n, f of A raised to I equal to
so
E2.
let's say let m be n such that f of A to the power m is E2. Then
E2 we can write it as f of E1.
f of E1, okay. Then
And then f of A raised to f of A whole raised to m is equal to f of A raised to m.
okay, fine. Then
So A raised to m will be equal to E1.
no, how? F of A raised to m is equal to f of A raised to n, right? That is what you're saying. Does that imply A raised to m is equal to A raised to n? Does that imply this?
No, sir, we haven't shown that it is 1, 1.
Exactly. F here is just any homomorphism. So this does not imply, okay, maybe I mark this by a red color that you can see the importance of it. It does not imply this. So what can you say about the order of FA?
It will divide order of A.
Exactly, that's the only thing we can say. Order of FA divides N. That for sure has to be true, right? I hope everyone agrees with this.
Yes, sir.
Is there anybody who does not understand this? Okay. Right. As of now, this is the only thing we can say, and you know why, right? because this implication is not true. When would this implication be true?
It will be one-to-one function.
Right. So if f is 1-to-1, then the orders would have to be the same, right? So it's just a small remark, and it will be part of a proposition that will show up later. Okay. So this out of its way. So this is all that we can say, right? Order of f8 will divide n. Then let's try to sort of dig into this more. Let's say I have a subgroup H of G1. What can we say about the image of H under F? I hope this notation is familiar to you, f of h. F of h just means this: collection of the set of all fh's or all h in capital H. Okay, this is the definition. Image of h under f. What can we say about this? So of course, one easy thing that I will say is this is a subset of G2. Okay. Can I sort of say more about it? And I hope by now it is clear what is the additional property I'm looking for. What is the question here? FH is FH
Subgroup of G2.
Subgroup of G2.
Subgroup.
Is this
Closure and inverse.
Yes, so let's try to maybe show closure. So what kind of elements will we have in F capital H? FH1 and FH2, right? Then what can we say about F1 into FH2?
F of H1 H2.
Of H1 H2. What can we say about this element?
It should belong to
F of
It should
H2
belong to FH. Because H1 H2 is an element in H, since H is a subgroup. Okay, so closure is clear. How about inverse? Let us pick an arbitrary element in F of H. Then
F of H whole inverse is equal to F of H inverse.
so you need to show that that element is in F of H.
Sir, because H inverse belongs to capital H, therefore F of H inverse belongs to F of H.
H in H is in H. H inverse also is in H. Therefore, F of H inverse is also in H. But as we by 2, point number 2 here in the same proposition, this is equal to FH inverse. Therefore, FH is a subgroup. Oh, sorry, I made a mistake here. FH inverse should belong to F capital H. Just make that small correction in case you're making it. Right. So basically we have proved that F of H will also be a subgroup in G2. There's one more thing. So something but almost the converse of 5. Almost. Let's consider a subgroup of G2. Let's call it K. How about F inverse K? I mean, once again, I'm not sure if you're familiar with this notation. What does F inverse K mean?
Set of inverse of elements of K.
But is F invertible?
Sir, only if it is 1, 1 and 1, 2.
Right. So, but this proposition does not make any such assumption, right? Says whatever we are proving is true for any homomorphism. Okay, so that basically tells me that you're not familiar with this notation. Let me define this. F inverse K is set of all H's all H's in G1 such that F maps H to some element of this K. Okay, that is how F inverse K is defined. It is called the inverse image of K in G1. Okay, so you can look at the definition. I hope you agree that F need not be invertible for this to be defined. Okay, so you take all elements in the domain of F, right, which F maps into this subgroup or subset that we are considering. Okay, remember, this notation applies to any subset K of G2. That K may be a subgroup or not, this notation still holds true. Okay, so the same question that we asked in point number 5 applies to point number 6. What do you think? Is F inverse K a subgroup of G1? Quick, anyone? Maybe let's start with closure. So what sort of elements will be there in F inverse K? Let's say K1, K2, P elements in F inverse K. What does that mean? What is the definition for any element in F inverse K? Is there any issues understanding this definition? Why is there a stunned silence?
Sir, can you explain this again?
This in the sense?
It means sixth.
Right. So, okay. F inverse K, this notation is not clear?
No, sir.
Okay. So F inverse K, okay, maybe let me take an example. One, 3, 4, 5, 6, 7, 8, 9, and let this be 10, 20, 30. Okay, so these are two sets. Consider them as two sets. And F maps A to B. The way it maps is F maps all these three elements to, let's say, 10, maps these three elements 20, let's say, and F maps these last three elements 7, 8, 9 to 30. Maybe I'll just include one for element 10. One more element 40. Right, and F is, as you can see, it's neither 1 to 1 nor on to. Is this example clear?
Yes, sir.
Okay. So now, yes, right. So what is F inverse of the set 10? Right. So if I want to find this out, what I'm looking for is what elements in the domain A get mapped to this set by the function F. Okay, so what all elements does F map to elements of this set?
1, 2, 3.
So that is F inverse 10. How about F inverse 40?
No element.
Empty.
No element, so null set.
5.
Okay, how about, let me take one more example. F inverse 10, 20.
One to six.
1 to 6. Clear?
Yes, sir.
Okay, this is called the inverse image. I hope all of you have understood this notation. Is there anybody who has not understood this? Please tell me now. We can maybe take another example to clarify this. If it is clear, then I hope the question makes sense at least. May not still be obvious. Right? So F inverse K will be some subset of G1. I'm interested in looking at whether this subset F inverse K is also a subgroup, given that this K is a subgroup. Okay, so again, I need to look at closure and inverse. For closure, what should I do? I should pick two arbitrary elements in this subset, F inverse K. Okay, so what is the defining property of elements of this set F inverse K?
Sir, it will be all the elements that map to K1 under F.
No. K1 and K2 are elements of this set F inverse K, right? This K1, K2 and this K are very different things. Okay, if the notations is confusing you.
No, sir. The notation is clear. Sir,
Okay.
I was telling that here K1, K2 belongs to F inverse of K, right, sir?
Right.
Then this implies that this will map to a set of elements H such that F of H is equals to K1.
No. Okay, let me stick to this notation.
Here AB belongs to G1, right?
Yes, A and B will belong to G1. But can A and B be two arbitrary elements of G1?
No, sir. F of A and F of B should be belong to K.
This belongs to K. Right? That is something we can say for sure. Okay. Now, in order to check closure, what should I check? I should check, does F map the element AB into K or not? Right?
Yes, sir.
If AB gets mapped into the set K, then by definition AB will be in F inverse K. Okay, so what can we say about F of AB?
F of A, F of B.
F of A into F of B. I'm just using the homomorphism property of F. Then what can we say about FA into FB?
Belongs to
F and F B are
Belongs to
in K.
K simply because Fa and Fp are elements of K and K is a subgroup. So we are done, isn't it? Okay. Similarly, inverse. Let A belong to F inverse K. So F of A is in K. Next,
F of A inverse.
F is here. F inverse is in also K, right?
Yes.
F A inverse is
F of A
F
whole
of
inverse.
A inverse.
A inverse is in K. Therefore, A inverse is in F inverse K. So we are done. Okay, we'll continue with this in the next class. Several more interesting properties of homomorphisms, and as we discussed a while ago, that homomorphisms will become more interesting if we put certain restrictions on F. Okay, and the restrictions that we almost have figured out is that F should be what kind of a map?
1 1.
1 1 and also onto. Okay, so those kinds of homomorphisms are what are known as isomorphisms. Okay, so more details on this and all other properties that we can derive if F is a homomorphism and bijective function, all of that will come in the next class. Okay, thank you. Stop here for today.
Hello, sir.
Yes.
Sir, I have a doubt.
Okay, go ahead.
Sir, Dn is a dihedral group of means n-gon, polygon with n side, right?
Right.
But sir, how can D1 and D2 be possible? Means in some example I have seen D1 and D2 are.
No. Okay, so I think there is a difference in notation. Although I'm not sure D1 and D2. Have you seen D1 and D2?
Yes, sir, D1 and D2. And sir, it is also that D1 is isomorphic to Z2.
D1. So one gone is line. D2. How did you say D2? That's interesting.
And sir, D2 is isomorphic to Z2 square.
Can you email me? Where did you find that?
Sir, on Wikipedia. Okay, sir, I will email you.
Sure. Okay. I would like to see their notation. What do they mean by D1 and D2? D1 would basically mean a point. On a point, what can you do?
Sir, the point is having infinite symmetries, right, sir?
Yeah, so that's why I'm saying why should it be Z2?
Yes, sir, that's I didn't understand.
Okay.
And also D2 is isomorphic to Z2 square. I mean, how it is.
Z2 would basically have only two elements, right? Rotation by 180 and identity. So yeah, I mean, as of now, I don't know the answer to your question, but I will try to look at it if you can sort of share the reference where you read this.
Okay, sir.
Okay. Yeah. Thank you. Any other doubts?
Hello, sir.